So, welcome back to the second part of the session of this morning. Sorry, maybe to pretend to be serious. Okay. I'm really excited about this one. Speculative decoding is an essential part of inference. I don't know, maybe at scale of what kind of providers such as OpenAPI use, but it's been on the news fairly recently. If you remember, like the Gemma 12b release, they also provided with MTPM, multi-token prediction support. If you read the headlines on sites like Hacker News in the last week, we saw a post from Xiaomi where they say that they claim to serve, I think it was a trillion parameter model with 1,000 tokens per second. That's the scale, without using custom hardware such as a Grok or Cerebrus, like special solution, because they exploit strategies such as DFlash, which we're going to talk about with Eldar today. So I'm really excited about this one. And just one more thing before we start, everybody knows Red Hat and IBM, like they've been incredibly active as a lab in research. I think a bit of an underdog in the sense that they do like a lot of interesting stuff that does not like end up in the news, especially here in Europe, but they do train good models with the Granite family. The Red Hat team is supporting actively the development of vLLM. They had a meetup in Milan in the beginning of spring, approximately, and like they've always been friends with Py4AI and PyCon and Python Milan as well. Daniele has been a speaker several times. He also wrote a book, but I do not like steal the space from Eldar. But anyway, so they're good friends, and we're glad to have them support us with the contents and the contribution that they gave us. So please join me in welcoming to the stage, Eldar. The floor is yours.
Yeah, thank you very much for the introduction. My name is Eldar Kurtić. I work as a research scientist at Red Hat and also Institute of Science and Technology of Austria. And the main topic of the research is inference acceleration through any techniques, like whether it's through sparsity, knowledge distillation, quantization, and of course recently with speculative decoding as well, because it became like a standalone tool to accelerate inference due to some very kind of great features relative to all other techniques. The idea for the talk today is that it's going to be like a tutorial style. So we're going to go through the background on what speculative decoding is all about, how it works, why it works, when it does not work. That's something that you should also be aware of. It's not like a golden bullet that's going to accelerate all of your inference workloads. And then I'm going to show you some examples on where to start if you're about to start tomorrow with speculative decoding. One also like additional piece of information that's relevant for this is that we will not go into the details of any specific speculative decoding algorithm. I'll just like reflect what are the main differences between like EAGLE-3, DFlash, MTP, and so on, just so you're aware of, because there is like a ton of like a very active research work in this area. So whatever I tell you now might not be like a very relevant in like a week or so. So basically, speculative decoding, and the main reason why it became very popular very recently is the fact that this is a lossless technique to speed up LLM inference. And contrary to quantization, pruning, knowledge distillation, all these other prior techniques, when we are deploying a model in a speculative decoding pipeline, there is no need for us to run like very extensive accuracy evals to convince our customer or the end user that the model is doing the right thing. So whenever we quantize the model, usually we have to follow up like with a lot of evals just to confirm that our model is still doing the same thing that the original model was supposed to do. With speculative decoding, there's no need to do that because there is a theory behind it which states that if we do it in a specific way that we'll see later on, we are guaranteed to get exactly the same distribution of the text as we would get without speculative decoding. So that's kind of the nice, cool feature. Of course, kind of relative to quantization, it comes at the cost. To do quantization, it's relatively easy. Like we can quantize a model like on a single GPU in like a couple of minutes, whereas with speculative decoding, we need to invest a lot of resources to train like a speculator model from scratch. So it's a trade-off. Speculative decoding is based kind of on the fact that it's using like a smaller model, which is called either a draft model or a speculator model, whose main task is to be very small and therefore very fast, and then to generate many tokens in advance, And then we have a larger model, so this is our target model, which verifies these tokens. And this is where where we come back to this like a lossless part, because the larger model is going to evaluate all of the tokens proposed by the smaller model, and therefore accept only those that it thinks that should be kind of like produced or like passed on to the user. And this gives us this lossless part because we get to verify all of the tokens before we provide them as the output. So it boosts performance without sacrificing quality, and there is also like, so every accepted token is guaranteed to come from the same distribution as if it was generated by the target model directly. So that's the great part of speculative decoding. So now I prepared like a kind of some visualization that we're going to go through just to illustrate how the pipeline looks like. So contrary to like the standard LLM inference, where we have just one large model, which is called our target model. In the speculative decoding pipeline, we are always deploying two models at the same time. The first one is the draft model, so this is a very small but like very fast model, and then we have our target model that we want to accelerate. The first phase of the speculative decoding pipeline is called like a speculation phase. So this is the phase where we have our draft model, and it runs the standard like a normal forward pass. We have a prompt, for example, the quick brown fox jumps. We pass it through the draft model, and we ask this model to speculate the next 4 tokens. And then the model is going to produce tokens. This is a hyperparameter, how many tokens we ask the model to speculate. And usually we pick this based on how accurate our model is. So there will be some, we'll talk a bit about the accuracy in the end. But this is like our choice that we have to come up with. So the model is going to do the standard like an autoregressive loop, generate 1 token, pull it back inside, generate the second one, pull it back inside, generate the third one, and so on and so forth. Once we generate all of the tokens with the draft model, we go to the second stage, and the second stage is called parallel verification. In this stage, what we are doing, we are taking all of the tokens together, like that the speculator model produced, and we are passing them through the larger model, through the target model, so that this model can verify the outputs that have been speculated by the smaller drafter model. So what's going to happen at this stage is that we already did the these 4 forward passes through the draft model. So we generated some outputs, and we got the probability distribution for each token. Once we do the forward pass through the target model, we will also get the probability distribution at each token place by the target model. And now our task is to compare these 2 probability distributions and see which tokens actually align between the draft and the target model, and based on their like alignment, we're going to accept them or reject them. So as kind of the great part of the LLM inference, whenever we do a forward pass through a model with n tokens, at each position we're going to get the full probability distribution of what the model thinks the next token should be, given all of the previous tokens in the context. And therefore, we compare the distributions from the target and the draft model at each of these positions. So for the first one here, I think it might be too small, but the draft model predicted like this token with like a certainty of 70%. The target model said 65. We compute the ratio between the two, so we take probability of the target model, we divide it with the probability of the drafter model, and then we get the ratio, which is called acceptance probability for this specific token. And this acceptance probability literally tells us how similar is the thinking of the target model and the drafter model. Given that 70 and 65 are very close, so the ratio is 93. So this means that we are very likely to accept this token at the output. We go to the next token. Smaller model said 40%. The target model said 38. So the ratio is 95. So we'll most likely accept this one. However, for the third token, we see that the drafter model assigned probability of 30%, whereas the target model assigned probability of 5%. The ratio is 0.17. So only with probability of 17%, we're going to accept this token. So what we do with these probabilities is now we take these like probabilities, which are called acceptance probabilities, and then we sample like a random number from like 0 to 1 uniformly and compare with this acceptance probability. What's going to happen most likely is that for the first 2 tokens where we have acceptance rate over 90%, we'll most likely accept these tokens, which means that the target model agrees with the drafter model that these should be the next tokens in the sequence. Whereas for the third one here, we have seen that the acceptance probability was quite low, 17%. So most likely we're going to reject this token. So at this stage, there is we go to the next part of the speculative decoding pipeline, which says that once you reject a token, you have to discard all of the follow-up tokens, because all of the follow-up tokens were speculated under the assumption that all of the previous tokens are correct, right? So that's kind of the standard autoregressive pipeline. So we're going to reject tired, and we're going to also have to reject the dog in this specific example here. And then there is the additional kind of cool part of the LLM inference is that the fact that I mentioned before, whenever we do a forward pass, at each position we're going to get a probability distribution of what the model thinks the next token should be given all of the previous tokens. So once we discard the token tired, we can use the probability distribution because we already have it from the target model and resample this token back. So we're going to say, just ask the target model, okay, what do you think the next token should be at this specific place? And then we're going to resample from the target model. And this gives us this additional +1 bonus token that we get from the target model, in addition to all of the tokens we accepted from the speculator model. And therefore, we kind of end up this a cycle of the speculative decoding with 3 new tokens that we generated. So now let's take a look at the breakdown, so kind of the cost breakdown of what would happen if we are about to produce 3 tokens in the standard autoregressive pipeline, so without the speculative decoding compared to what we would get with speculative decoding. So in the standard pipeline without speculative decoding, in order to produce 3 new tokens, we have to run 3 forward passes through the larger model. So that would be 1 forward pass, 2nd forward pass, 3rd forward pass. Here, I'm assuming that all of these forward passes cost the same amount of time. Usually there is some small difference, right, because we are adding 1 token at a time. But on average, let's say, for simplicity, because now we're just doing some napkin math, so let's just assume that they are the same. Whereas in the speculative decoding pipeline, we had to do, in order to produce these 3 tokens, we had to first speculate and do 4 forward passes through the drafter model, indicated by the blue blocks, and then we had to do 1 forward pass through the target model. Kind of this was a verification pass. So this means we had 4 forward passes through the drafter plus 1 forward pass through the target model. Given that when we are designing speculative decoding models, we are always designing them in a way that the drafter model is extremely small relative to the original target model. So that's kind of the main driving force behind the speculative decoding that we have to respect. If that's not respected, then most of these things are going to fall apart. And that means that now we can kind of, in this a napkin math experiment, we can assume that because our model, drafter model, is much smaller than the target model. Therefore, its runtime is very small, so we can drop the 4 times forward pass to the drafter model and kind of compare roughly the costs of these 2, which are 3 forward passes through the target model versus 1 forward pass through the same target model. So kind of this is just of course, we are dropping a lot of things here, approximating a lot, but this is just to give us the feeling for the order of the improvements that we are about to expect from speculative decoding pipeline. Later on, you will see that it's not always 3x. There is a lot of room for going above and below this number, but this is just kind of to give us a rough estimate. And this is the first part that the speculative decoding relies upon. So the drafter model has to be so small that its runtime is negligible relative to the runtime of the larger target model, so that we can make this approximation. The second thing I also did on the previous slide is that I used the same kind of block size, to indicate the same runtime of 1 forward pass in the standard, the autoregressive pipeline, and 1 forward pass in the speculative decoding pipeline. But if you look previously, 1 forward pass in the speculative decoding pipeline means we are doing k tokens in parallel, right? Because we are verifying all speculated tokens at the same time. So we are doing, in the normal autoregressive pipeline, we are doing 1 token at a time. In the speculative decoding pipeline, we are doing n tokens at a time, where n is the number of tokens we are speculating. And here comes the second part, or kind of the second feature of LLM inference that speculative decoding relies upon, and that's the fact that for most of these workloads, the pipeline is bounded by the memory bandwidth, not by the compute, at least for the use cases that speculative decoding cares about. What this means in practice is that if we take, for example, Llama 3.3 70B model, we deploy this model and then we run some prompts through the model, or kind of just look how the batch size influences runtime. So for example, what we are looking here is what is the slowdown of the one decoding pass through the Llama 70B model once we increase the batch size from 1 to 64. So we start with 1, we increase the batch size to 2, then to 4, we don't see any slowdown. So it's the same amount of time to run batch size 1 and batch size 4. Then we go to batch size 8 and 16, we start seeing 5%, 8% slowdown, and once we push to the very end of the spectrum, 32 and 64, we see 20% and 50% slowdown. So what this means for us in practice is that now this verification pass in the speculative decoding, if our n, so number of tokens, is small enough that fits in this range here, where we don't see any slowdown, that means that this forward pass costs the same amount of time as the forward pass in the standard normal autoregressive pipeline where we are generating 1 token at a time. And therefore, that also influences the choice of the n, of the number of tokens we are speculating. It always has to be kind of dependent on the setup where you're deploying so that you're aware of this trade-off here. And this already gives us a very good baseline for speculative decoding as well. Even if you assume all of the tokens, for example, are rejected, we will always get this +1 token, right? Just by doing a forward pass through the target model, because we always get this +1, even if we reject at the first position, we'll get this +1. Whereas in the normal pipeline, the highest amount of tokens that we can get is 1, right? Because standard autoregressive generates 1 token and then has to repeat the loop. And here, if we are in this regime, even if we reject all of the tokens, we will still get 1 token from the target model. So our baseline is exactly the same as in the standard autoregressive pipeline. And if our speculator is good at least at the first token or the second one, and we always will be adding just to this +1. So we get 2, 3, 4, 5, or whatever is the accuracy of our model. And that's kind of the second part that the speculative decoding heavily relies upon. We always need to be in this kind of a memory bandwidth regime where compute is more or less for free. And this is happening mostly because in LLM inference, whenever we are bounded by the memory bandwidth, the compute that's happening inside tensor cores is almost for free. So it costs the same amount of time if the batch size is 1 versus batch size 4. So it takes the same amount of time for GPU to process this. And this is what we kind of leverage here to pack more tokens in this verification step. So now, if we take the same model and we send a lot of prompts, which I call here math reasoning, but they are basically from GSM-8K, Math 500, these standard benchmarks. And then what I'm measuring how latency changes with respect to the number of requests per second that are coming to the server. And I'm deploying the model with and without speculative decoding. And usually what we see here is that once we apply speculative decoding, we start seeing speedups anywhere from 1.3x up to 2.7. And this is exactly 2.7 kind of relates back, because this is the same example I used before. It's not 3x. 3x was based on our napkin math, where we kind of assumed that 4 forward passes through the draft model cost negligible amount of time, but in the real world they actually cost some runtime. So it's not like a 3x. It's amortized with this additional ratio. The other part of the story with speculative decoding is to also be aware of the fact that speculative decoding is not like a golden bullet, so it will not always bring you speed ups in your deployments. And this Qwen-3 32B model is a perfect example here. So here, what I'm doing, I'm taking this 32B model from Qwen, and I'm sending a lot of coding prompts like human eval, MBPP, standard complete this function in Python or some other language. And then I'm like sending different number of requests per second and measuring the latency of the model with and without speculative decoding. What we see in this specific use case is that the highest speed up that we get is usually at the beginning, when we have like very, very low number of requests coming to the server. And as we increase the number of requests, at some point we're going to cross a boundary here and get into the regime where speculative decoding slows down our inference. This means that you are entering like a heavily compute-bounded regime. So whenever we are doing inference with LLMs, there are these two regimes. The first one is like memory bandwidth bounded. The second one is compute bounded. The memory bandwidth bounded regime is a regime where, as I mentioned before, compute is mostly for free, and the only cost we are paying is the cost to load the weights from HBM into SRAM, into tensor cores to do the matmos, but the matmos are for free in this regime. So the main cost is just moving the weights around. In the second regime, this second regime kind of steps in when we have large enough inputs to keep our GPUs busy doing matmos. Once we get into this regime, then the compute becomes like actual bottleneck and the memory bandwidth is not the problem anymore. And with this specific setup, we are kind of entering this regime as we are increasing the number of requests per second. Our server becomes more and more busy doing matmos and not doing the loads of the weights. And therefore, we enter the regime where speculative decoding is kind of hurting our inference performance. So, if you're about to start with speculative decoding and you would like to try it on your own, the first place I would point you to is Speculator's library within the vLLM project. So, as mentioned before, vLLM is like the de facto industry standard for serving LLMs these days. And as part of the project, like it comes with all the bells and whistles, like which are like optimizing the normal flow. We also have a couple of additional libraries within vLLM project, kind of to bring additional gains, like on the inference side, such as, for example, LLM compressor for quantization and speculators for speculative decoding. The first feature that we added to speculators and that is available here is like converting speculative decoding models to like a format suitable for vLLM deployment. This was like very important because many speculative decoding many papers on speculative decoding started appearing in the last couple of months. This means that there is no like a standard way on how to save these checkpoints in a format that is that can be used and ingested by vLLM. So the speculators library helps you like in taking any Hugging Face available, like any like a speculative decoding model available in Hugging Face from various research papers and converting that into a format that vLLM understands. So you can just take the model and deploy it in the vLLM. However, just taking the off-the-shelf models specifically for speculative decoding pipeline is not always the right choice, as we'll see later on. What you would usually like to do if you have like a custom data set that you care about, you would like to train the speculator on your own data set, because that's the best way that you're gonna squeeze the last bit of the performance from your speculative decoding pipeline. And that is mostly because in this like a speculative decoding regime, what we are trying to do, we are trying to train like a small draft model to imitate the teacher model, like our original like a target model, to try to predict the text in the same way. This is why, and these like a drafter models are, as I mentioned before, they're like a really, really small models. So we cannot expect from them to be good at all tasks. Because if they are good at math, at coding, at multilingual prompts and so on, we would never need large LLMs, right? Like we would just like deploy smaller models. And this is the main reason why usually the best speedups are obtained if you take the smaller model and then you train it on your own data set that you care about. Because most likely your application does not require very good performance on math and very good performance on like maybe language translation or something like this. And the speculators, for that sole reason, speculators does support training from scratch. It provides a Hugging Face, like a compatible format, so you can use these models even without vLLM. And the models are exported into formats suitable for vLLM. And the other part of the story is that the speculators implements like all of the popular state-of-the-art speculative decoding techniques, and most of these are implemented in collaboration with the original authors of these papers. So there's like a 100% kind of match to whatever they said in the paper. That it's because usually there is some mismatch on what they actually say in the paper versus what is available in like open source libraries. And the most popular techniques right now are like EAGLE-3, pEagle, DFlash, and MTP. Most likely, community is now converging to the DFlash because it has some nice features that we will briefly talk about later on. So, how to use speculative decoding? As I mentioned before, the first part is like, if you have your own internal kind of domain-specific data set, you really want to train a speculator from scratch, because that's the best way kind of to like squeeze in all of the possible performance gains out of it. Whereas if you're looking for an easy entry point, you just want to try speculative decoding to see how it works in general, like to set some kind of like a reasonable baseline. And then you can start building like off of that. You don't need to invest all of your resources into training one from scratch. You just can take some like decent baselines which are open source. You can go to Red Hat AI's Hugging Face hub. So this is basically our hub where our research and engineering team are like constantly releasing speculative decoding models. They're usually a really good choice for you if you're like looking at like some general capabilities. So if you want like a decent model that works across math, across coding, across multilingual, summarization, all these different use cases, as I mentioned before, it's not going to be the best possible. So they're not like a benchmarks to be the best at math, the best at coding. They're like a good enough like to be like some kind of solid baseline, and then you can build on top of them, like and specialize them more if you really need them. So let's take the first pathway here. If we are about to train your own speculator model from scratch, I'm just gonna like flash like some like a scripts on how to do it, just kind of to explain you what is the usual pipeline, kind of to get from scratch to like a speculative decoding model that you can deploy tomorrow in vLLM. The first part of this pipeline is to prepare a target model's responses to train on. So as I mentioned before, speculative decoding is all about training a drafter model to perfectly imitate the larger model. In order to imitate the larger model, we need to get some text from the larger model first, right? Because usually if you go to Hugging Face Hub, you look at any chat data set, you will see like question-answer pairs, like input and output prompts, but these output prompts are usually generated by some other model, either by some version of ChatGPT, Claude, or whatever, like some model that dataset creator chose. So what you want to do, you want to take this example, discard all of the outputs, because like these outputs are generated by the model that is not relevant to you, but you want to preserve the input prompts. And then you're going to take all of the input prompts, you're going to pass them through your target model, and you're going to collect the completions from the model, because these completions are going to be very different if you're taking them from Llama versus Qwen versus Mistral or any other open source model, because all these models have like very different way that they are answering to user questions. In this specific example here, I am taking like a Gemma 4 31B instruction tuned model, and I'm using like prompts from Magpie and UltraChat datasets. So you can basically just collect responses, take the prompts from these two datasets, and then collect responses from the Gemma model. And that's like the first step where you prepare your own dataset. If you have your own data that you care about, what you want to do here, you want to like pass in the prompts that you care about. If it's math, it's going to be some math prompts. If it's coding, it's going to be coding prompts, and so on and so forth. The second step, so whenever we are training speculative decoding models, all of these techniques for speculative decoding, they are based on extracting the hidden states from the larger model and then combining them in some way and then predicting what the next token should be based on that. So EAGLE-3, DFlash, they all have different ways of pulling the hidden states from the larger model. But the main important point and common point between them is that you need to specify from which layers you want to pull the hidden states. That's kind of the hyperparameter that you usually have to decide on your own. Given that we are extracting the hidden states from the larger model, there are two ways to do it. One is offline, the other one is online mode. The offline mode would mean we take all of our prompts, we run them through the model, and then we observe and collect all of the hidden states from this specific model, we save them, and then we train on that. This pipeline was the first pipeline that got supported in speculators, and it's still available. However, it's not a well-recommended pathway, mostly because you have to store the hidden state somewhere. This grows extremely in terms of the disk consumption. It grows kind of very quickly with the number of the hidden layers that you want to pull states from, because if you recall, all these hidden states are like very large tensors, which are like a batch size times the hidden size, and hidden size was like usually a couple thousand with these large models, and all of these are like BF16, so 16 bits per parameter in the vector. So what we decided to do in the end is like to do the online approach. So the online approach is we host a model like with a vLLM on a couple of GPUs, and then we kick off the training in the other process, and then this other process sends the prompts to the vLLM server. vLLM server runs the model and then extracts the hidden states and gets them back to the model, which is then training on those hidden states. This is of course slightly faster than the offline approach, right? Because we have to do online generation of the hidden states, but it's much more friendly to the disk usage, because like disk usage grows very quickly, kind of like it goes like to like tens of terabytes just for like a Qwen 8B model. So in order to do this, we kick off the vLLM server. We specify which target layers we want to pull the hidden states from. Usually, like this is some kind of like a distribution you like take from the first to the last layer, like with some spacing, depending on how many layers you want to pull the information from. And then these are like just some like hyperparameters for the vLLM server, like what's the maximum model length that we want to support, what's the tensor parallel, what's the data parallel size, like all like vLLM server specifics. And then we kick off the training process. So now we have vLLM server running on a couple of GPUs. We are on the second part. We are like in a different process, doing a standard like PyTorch FSDP training. Nothing like fancy about it, except that now the only thing we have to specify is how do we want to handle the data that's coming from the vLLM server. Because we are doing online generation, we don't want to like store a lot of data on our server just because of the disk usage problems. What we're going to do here is like whenever there is a missing completion or like a missing hidden states on our data path, we're just going to generate the new one. So ask vLLM server to generate, and then whenever it generates, it's going to delete it. So we're just going to dump them away. If we're about to train for multiple epochs, then we have a larger disk storage, and we could play with this a bit and then maybe preserve a couple of these so we don't have to like redo every single epoch new generation. And then we have the standard like LLM training hyperparameters, like a learning rate scheduler, type of the learning rate, number of epochs, blah blah, all the standard stuff. Once we are done with training, we're going to get a checkpoint which is already like fully supported in vLLM. So we're going to just run vLLM serve. Here we are specifying we want to do it on 2 GPUs with tensor parallel of 2, and then we specify the speculator model that we want to deploy. And yeah, vLLM is going to pick the best pipeline to run this for. If you don't want to do any of this, you don't have custom data set, you just want to take like a generally good one like across many different domains. As I mentioned, you can go to Red Hat AI's Hugging Face Hub. All of these are like fully open sourced. Usually you'll find a lot of EAGLE-3 models because that was the previous state-of-the-art technique for this. And recently we pushed over and started like shipping more DFlash speculator models. One of the huge acknowledgements, given that Speculators is a very early stage project, is that, for example, Poolside team already adopted Speculators library to train their own DFlash for their like a model release. If you open any of these models, model cards on the Hugging Face Hub, at least the ones from Red Hat, they're coming with like very extensive set of evals, so you're aware of the quality of the checkpoint that you're about to deploy. So usually you're going to see like some huge table like this, where we run prompts from different evaluation data sets, and then we compute like the acceptance rates for each position. This specifically here is like a DFlash model, which predicts 8 tokens at a time. So we have acceptance rate for each position, and then the last column gives you the average acceptance length that you should expect from this model. So for example, human eval math reasoning, as you can see, our data set was more specialized to these kinds of prompts, and therefore we get like on average we get 5 tokens by just doing one forward pass through speculative decoding, whereas the data set we trained on was not that well suited for summarization. Then you see slightly lower, like 2.5 tokens on average getting out of the speculative decoding pipeline. And then you will see like some plots like this, which are basically showing you what's the speed up you should expect in different use cases, just so you're aware of what you're using. And yeah, the last slide is regarding composing speculative decoding with other inference acceleration techniques. That's the very cool part, because speculative decoding is completely orthogonal to like knowledge distillation, pruning, quantization, and so on. So whatever you used before, you can just like slap speculative decoding on top of it, and it's just going to bring additional speed up gains. One example here is like a JAMA 431 billion model. On a human eval prompts, we are measuring the inter-token latency, how inter-token latency changes with respect to the number of requests that are coming to our server. And this is the baseline without any speculative decoding, without any optimizations. Once we push and do FP8 quantization, we get the red line here. Then if we do EAGLE-3 speculative decoding, we get the green line here. Then we do DFlash, we lower the latency even more. And then once we combine DFlash and FP8 quantization, we get like almost 6x faster inference, just kind of due to the fact that we can combine multiple different acceleration techniques to generate the tokens. And yeah, that would be all. Happy to take any questions.
Right on time. Thank you very much, Eldar. That was great. If you just, in the meantime, while we take questions, you can also scan the QR code to provide feedback on these talks. I know it's unnecessary in this circumstance, but still I need to collect some data about the preferences. Still, floor is open for questions.
Okay, so I have a question. Like, what if, from what I understand, you're basically training a smaller model by exposing the hidden states of the larger model and making the smaller model reproduce those hidden states. But what if the larger model has a way different architecture? For example, let's say the larger one is a mixture of experts, and you're trying to train a smaller one which is not.
Yeah, that's a great question. So, as a matter of fact, this surprisingly works really well, because right now, most of the checkpoints, for example, EAGLE checkpoints, are basically just using the llama architecture. And then we are training like a 3-layer llama architecture, but we are using that to kind of like predict like a next token and hidden states of, I know, like a DeepSeek, Mistral, or whatever. Yeah, it works just fine. The original papers used to like copy over the architecture of the original model, and then we did some ablations. We never found any significant reason to do that. And on the inference side, it makes our life much easier to optimize kernels for one architecture than to support many of those. And it works just fine. Yeah. One note to that is that we are recently started adopting Qwen architecture instead of Llama, because Llama is a little bit outdated. Qwen has like some like QK norms and all these like additional fancy tricks to stabilize training even more. And it seems like it works as well, as good as it works in training. It also works for speculative decoding. So we are slightly moving towards Qwen. We are seeing maybe half 0.5 increase in the average acceptance length just by kind of changing to that. So it's still like an open question whether there's like even better architecture than Qwen, but so far the Qwen seems to be working just fine. Yeah. You're welcome.
And you can do this because they have the same hidden dimension?
So yes, you just design, when you design the speculator model, like you use the architecture of Qwen, but you like play with the hidden size to match the hidden size of the original model. Yeah, and then usually there is in all of these like a speculative decoding pipeline, there is like FC layer in between. When you pull the hidden states from the larger model, there is like FC layer which gets trained along with the speculator to map the hidden states from the larger model to the space of the smaller model.
So FC fully connected,
yes,
right?
Yes,
okay.
yes, fully
connected. But so it's trained from scratch or just fine-tuned?
It's trained from scratch.
Okay.
Yeah.
Any other questions? Really? Sorry, I couldn't see you from back there.
I think it was news from like a few weeks ago that they released the Gemma diffusion. Do you think diffusion might be like a new development in this kind of speed up in models?
Yes. So diffusion is like a very attractive topic, mostly because, for example, the DFlash here is basically like a diffusion-like type of a speculator, because it predicts like a block of tokens instead of one. So the original like speculative decoding came from the idea of let's deploy just small LLM, and then which is like much faster, and we're going to generate one token at a time. The problem with one token at a time is that this is autoregressive. You have to load all of the weights, do one token, load all of the weights again, load the stack. Yes, DFlash and like all this like idea behind diffusion models is basically now we're going to predict a block of tokens. So all of the main reason why DFlash is much better here in the plots than EAGLE-3 is because it's predicting either 8 or 16 tokens in a single forward pass. This means it's a little bit harder to train it, like, you know, to get there, and it has to be slightly larger model than EAGLE-3. So if you take on average DFlash size of a DFlash, it's probably 50% larger than EAGLE-3 because it's like doing much harder task right now, but it's giving you more tokens at the output. So there is kind of some kind of like a trade-off between the two. So you always have, like, usually we do like some kind of benchmarks to estimate what is the roughly size of the model, given the expected acceptance length that we're going to get from it, just kind of to know how to design it properly. And yeah, kind of, even though the diffusion in the DFlash is very simple, it's doing just one step, so it's not like doing this standard, like as you see in images, like, you know, multiple refinement phases, but this is only like for efficiency purposes, because it would be very expensive to do it multiple times, so it's doing just one pass. Yeah.
That's far away. No, but we need to record them for videos.
Thank you. I mean, I arrived a bit later, so sorry if you already said it, but what about using speculators for speculators?
So the idea of the speculators is that they have to be really, really small models, and therefore they're not really good at a lot of tasks. So that's kind of the main kind of like a drawback of this technique. So it really has to be specialized for something. Usually we are deploying LLMs to be good across many different domains. And then kind of in such use case, it's not possible to use smaller model. You know, you have to deploy DeepSeek or like a Quant32B because you really need to get some like high accuracy on some specific task you care about. If you happen to have like a smaller model, yeah, this is gonna all work. It's just gonna be even larger gain.
Sorry, can you repeat?
So if you have like a specific use case, for example, you need Quen, I know, like Quen model on a specific task, but you are able to like your original LLM is like very small just by design because your target task doesn't need like 32 billion parameters to run. Yeah, speculative decoding is just going to work the same. You just have to design the size of the speculator to be maybe 10 times smaller than whatever your original like target LLM is in order to get the speed ups out of it.
Yeah, but sorry, like, my question was, what about using an even smaller model to
speculate?
You mean
in addition to the two models?
Like using a speculator for the speculator. Like, how much can you go down?
Yeah, that inception, I'm not, yeah, it might go too deep. I'm not sure how that would look like.
Because, like, what is the point in which it stops being
yeah, I mean, it might be worth trying, but I really can't tell much. Because, yeah, I mean, the main problem with speculators right now is that they're already not, it's really hard to pull more than 3 to 5 tokens out of them. So they're already very small relative to that. So even if you design even smaller model, you drop to like 1 token maybe, and that makes it like very hard to get efficiency gains.
Like diminishing returns.
Yeah.
Thank you a lot.
Yeah, you're welcome.
Yeah, I have a very quick question. How small are these very small models?
It's usually 10 order like 10x smaller than the original model. That was
so
maybe
still, I mean, if you have a 70 billion parameters, it's still 7 billion parameters. So it's something that kind of needs more than one GPU. So it still kind of needs an optimized inference, even for that. Okay.
Yeah, exactly. Yes. And one thing that we started adopting, because once you go like 10x smaller than the original model, one bottleneck that I haven't talked about it here, but one bottleneck that arises is the fact that your input embeddings are becoming like a majority of the weights of your speculator, but you usually don't need all of the input embeddings for like, because your speculator is going to be good at math, and your like a vocabulary size is maybe 256K, but in those 256K, there's maybe only 32K of relevant tokens. Everything else is just like never used. So what we also do in the pre-processing step, we take the data set that you can. That's why I said like this should be like the best thing is like if you have domain-specific data set. So we would take your data set and then we would literally like tokenize the entire data set and like plot like a histogram of tokens. And then we would take give us like how large vocabulary I need to preserve 99% of the tokens in the data set I care about. And usually what you would see is that like this reduces your like a vocabulary size from 256K to maybe 32K or so. So then you get like additional kind of speed out of that, because now we have smaller model, you can fit like more requests.
Thank you.
There's time for one last question. There you go.
So thank you. Just a curiosity about the efficiency from the energetical consumption. So from what I grasped, I expect that if the small model is well trained and properly trained, the inference of the bigger model will be, let's say, more efficient. We will validate more tokens. So I expect that the energy consumption also could benefit if the smaller model is well trained of this, and not just the timing consumption. So you speed up the time, and from the time point of view, but you also gain on energy consumption. Is this true, and what is the bottleneck or the main limitation to this?
To be honest, I never did any energy measurements so far. Usually we optimize for like latency, throughput, and these metrics. One thing that could happen, at least from what I kind of roughly have seen, is that like energy measurement might be kind of directly correlated to the flops that you're doing in your pipeline. And in this specific case with speculative decoding, you're doing a little bit more flops. Actually, no. Compared to the normal pipeline, you're doing less flops because you have a smaller model. But it's not for free because you have the forward pass to the smaller model, then you have slightly larger like this like parallel verification phase. So it might consume a bit more than the normal like a pipeline, but probably not something super extreme. Yeah, just because it's a much smaller model, which does not have that many flops. It's like 3-5 layers. So. Yeah.
But in principle, if I guess, and I'm not sure it's something that is true, but if the smaller model is very good, in principle, you need to invoke less time the bigger one. So at the end, maybe in some time, we will reach a point at which also from the energetic point of view, it will be convenient. I guess. I'm not sure.
I mean, that's definitely true, because then you will be like, if your speculator is a good model, you will be accepting on average like 5 tokens per iteration. For example, with DFlash, that's like very often if you have like specialized case, you will be accepting like for the cost of 1 forward pass, you'll get 5 tokens, which is like 5 times less flops in the end to do so. Yeah, probably. But yeah, I never did any measurements of that kind, so it's just speculation.
That's way. Thank you.
Yeah.
Let's give Eldar another round of applause.
Thank you.
Thank you very much.